Have you ever looked up at the night sky and felt, just a profound sense of wonder? Not just at the stars themselves, but at the grand, unseen forces that truly orchestrate the cosmic dance of galaxies. We see them spinning, we see them clustering into these vast cosmic webs, yet so much of it seems to, well, defy our sort of conventional understanding of gravity and visible matter.
Right. It feels incomplete somehow.
Exactly. It's almost as if there's a hidden maestro. A grand conductor operating behind the scenes, pulling strings we can't quite perceive.
A hidden architect, perhaps.
Yeah, I like that. Okay, let's unpack this then. Today, we're embarking on a deep dive into a truly revolutionary perspective. It's one that challenges some of our most deeply held assumptions about the cosmos.
And offers some pretty surprising answers.
It really does. Our exploration is anchored in a groundbreaking paper that's poised to shift paradigms. It's called The Dark Plasma Universe as the Template for the Ordinary Matter Universe, published just this September 2025.
And the author behind it is Alfred Jay, a name we'll be mentioning quite a bit, I imagine.
Definitely. His work is central here. Our mission today is to thoroughly explore this profound idea, the idea that dark matter isn't merely, inert and invisible particles just sitting there, not just passive gravitational filler.
Right. The standard picture is often just extra mass.
Exactly. But Alfred Jay posits it as something active, something dynamic, a dark plasma, and he suggests it functions as a fundamental template, almost like a ghost universe.
A ghost universe, influencing the visible one.
Precisely. Subtly influencing and actively shaping the visible universe through its own complex energetic dynamics. We're going to uncover how this dark plasma provides the gravitational blueprint and hidden dynamics for literally everything we see.
From the biggest structures down to individual galaxies.
From the largest cosmic filaments down to the spin of individual galaxies, yeah. By the end of this deep dive, you'll not only gain powerful insights that hopefully connect the dots on some of the universe's most perplexing galactic mysteries.
Those head scratchers.
Exactly. But you'll experience those aha moments about the universe's hidden mechanics and the surprising forces truly at play. You'll walk away with a quick, yet remarkably thorough grasp of a truly cutting-edge scientific theory, one that could genuinely redefine our cosmic understanding.
It's definitely a big idea.
It is. So here's where it gets really interesting. The foundational idea Alfred Jay presents is that dark matter isn't just stuff sitting out there.
Right.
Not just a passive presence adding invisible weight to galaxies. It's dynamic, it's active, it's a dark plasma. What's the core of this mind-bending idea? And how does it fundamentally change our view of the cosmos? It feels like it moves us beyond just more gravity to something else entirely.
Well, that's exactly it. The central premise, as Alfred Jay really articulates it, is that a dark plasma isn't just a theoretical possibility floating around. It could actively, directly influence structure formation. We're talking cosmological scales here.
Okay, so not just sitting there, but doing something.
Right. This isn't just a minor tweak to our understanding. It represents a fundamental shift, really, in how we perceive the very fabric of space and the forces within it. I mean, if you think about known plasma dynamics, how charged particles interact under electromagnetic forces, right?
Yeah, like in the sun or fusion reactors.
Exactly. A dark plasma would likely exhibit similar behaviors. It would impact things like density, temperature, viscosity within the universe, much like ordinary plasma does.
But in the dark sector.
Precisely. On a scale and with characteristics unique to this hidden dark sector. And what's truly fascinating here, the core of it, is that these dynamic dark structures wouldn't just sit there as static gravitational wells, simply pulling things in.
Like the old dark matter picture.
Kind of, yeah. Instead, their internal plasma dynamics would actively shape ordinary matter structures. Now, not through direct electromagnetic interaction, that's key. Our ordinary matter wouldn't feel dark electromagnetism.
Okay, so how then?
Through persistent gravitational forces. Imagine this. The dark plasma is constantly churning, flowing, organizing itself maybe into currents or shells.
Right.
And these motions create subtle but powerful and long-lasting gravitational disturbances. This mechanism then provides an additional cause for the rotation of ordinary astrophysical objects.
An additional cause. So not replacing existing ideas entirely, but adding a new layer.
Potentially, yes.
Yep.
That rotation is transmitted from these hidden dynamic dark sectors to the ordinary matter sector, mainly through their gravitational interactions. It acts as a kind of unseen scaffolding.
The gravitational blueprint and hidden dynamics you mentioned?
That's the phrase Alfred Jay uses, yeah. It dictates the movements and structures of the entire visible cosmos. It's like discovering the conductor of that cosmic orchestra you talked about earlier.
Oh.
But Wanda doesn't just wave a baton, but actually moves the instruments into place, shaping the music through physical interaction, albeit gravitational.
So this isn't just theory then, just ideas on paper. Are there hints or parallels we've observed? Or maybe experiment with, something that gives this idea some grounding, suggesting we're not just, pulling this out of thin air.
Exactly. And there are. We have tangible evidence and perhaps surprisingly laboratory analogies that offer really compelling support for these ideas.
Laboratory analogies for cosmic dark matter.
Yeah, it sounds unlikely, but consider dusty or complex plasma experiments. These are done both here on Earth and under microgravity, like up on the International Space Station.
Okay, what are dusty plasmas?
They involve tiny charged dust particles suspended within a normal plasma. What's remarkable is that these systems, using fluid models, spontaneously develop voids and complex web-like structures.
Web-like structures, like the cosmic web.
Strikingly like the vast cosmic web we observe in the universe, yeah. It provides this tangible experimental parallel. It suggests that plasma dynamics, even in a controlled lab setting, can create complex, self-organizing structures that really do mirror cosmic pattern.
Wow, okay, that's unexpected.
Isn't it? And furthermore, if a cosmic dark matter web does exist, and we have strong evidence for it, and if dark matter is, as proposed, in a plasma state, then it's immense threads.
The ones we see indirectly through gravitational lensing.
Yes, those ones. And the ones vividly depicted in computer simulations, well, those threads would naturally be composed of this dynamic dark plasma. Ordinary matter, then, isn't just randomly scattered. It overlays these dark plasma threads.
Drawn in by gravity.
Exactly. Drawn in and concentrated by their powerful gravitational attraction. But here's the critical part, the dynamic part. These dark plasma dynamics cause these vast dark filaments of the cosmic web to rotate.
The filaments themselves are spinning.
The theory suggests yes, and observations are starting to back this up. As they rotate, they exert a gravitational tug on the ordinary matter filaments that are sort of intertwined with them,
Making the visible stuff rotate too.
causing them to rotate as well. And this isn't just abstract theory. We have actual observations of things like vortexes, Mach cones, shock fronts, and dark matter distributions, suggesting it's not just sitting there quietly.
Like ripples or wakes.
Something like that, yeah. For instance, some elliptical galaxies show these faint traces of concentric shells, which could very well be tracing these underlying dynamic dark plasma structures. We'll come back to those shells later. They're fascinating.
Okay.
And these flows of dark plasma, they're thought to be channeled along magnetic field lines. This strongly suggests the existence of something called dark Birkeland currents.
Birkeland current. Those are electrical currents in space plasma, right?
Right.
Like with the aurora.
Exactly. But these would be dark Birkeland currents, huge invisible rivers of dark plasma flowing along magnetic fields in the dark sector. And they would quite literally drag ordinary plasma along with them,
Right.
but through gravity, not electromagnetism.
Okay, so these cosmic filaments, these vast highways of matter, they're not just empty space with some galaxies dotted along them. They're incredibly complex structures. And the composition you mentioned, the paper gets specific about that, right? Hinting this dark plasma is really prevalent.
Very specific. It's not just a minor exotic component in this model, it's fundamental. According to researchers exploring these ideas, about half of all the matter in the entire universe is believed to reside within these monumental filaments.
Half. Wow.
Yeah, half. Now, if we assume, and it's a reasonable starting assumption, that the mix of plasma in these filaments is generally consistent with the overall composition of the universe, or at least our local patch of the multiverse,
Okay.
then their hypothesized composition paints a fascinating picture. Roughly 15% ordinary plasma, the stuff we know. Another 15% is thought to be this active dark plasma.
Equal amounts. Interesting.
Roughly, yeah. But then a significant 70% is termed pseudo or dormant dark plasma.
Pseudo or dormant, what does that mean?
It basically refers to dark matter particles that aren't actively ionized or interacting electromagnetically at that moment. They're maybe neutral dark particles or just not participating in the currents right then. But they still exist within the overall dark plasma environment, influenced by its gravity and its bulk dynamics.
So still part of the system, just not switched on electromagnetically.
That's a good way to put it. This distribution really underscores how pervasive, and fundamental the dark plasma concept is in this framework. It suggests it's the dominant form of matter, especially in these large-scale structures, even if only a fraction is actively behaving like a charged plasma at any given time.
So, okay, this dark plasma, it's not just a carbon copy, right?
Right.
Not just a mirror image of the ordinary plasma we see in the sun or in fusion experiments here on Earth. The paper by Alfred Jay highlights several key differences, things that make these dark sectors unique and, I guess, crucial to their proposed cosmic role. What truly sets them apart from our ordinary matter universe?
This is indeed a crucial distinction. It goes right to the heart of why dark plasma can behave in ways ordinary plasma often can't, especially on these vast cosmological scales. While dark sectors are similar to the ordinary matter sector in that most of their matter is proposed to exist in a plasma state, there are fundamental differences proposed.
Like what?
Well, firstly, the rate of ionization, the process of creating charged particles, would likely be significantly higher in dark sectors. Think of it this way. In our universe, you need a fair bit of energy to strip electrons from atoms to create plasma.
Right, high temperatures or radiation.
Exactly. In the dark sector, the conditions, perhaps due to different particle properties or energy levels, are proposed to be such that achieving and maintaining an ionized state for dark particles is much more common, much more prevalent.
Easier to make and keep dark plasma.
Potentially, yes. Secondly, and this is really important, because of a hypothesized weaker electric charge for individual dark particles.
Weaker charge, how does that help?
Well, it means that plasma instabilities, things that can quickly disrupt structures and neutralize charge separations in ordinary plasma, would be largely suppressed.
Ah, so the plasma is more stable.
Much more stable on large scales. In ordinary plasma, powerful instabilities can just dissipate structures, make everything neutral again very quickly. But in the dark sector, this weaker charge acts as a kind of cosmic shock absorber.
Okay.
It allows plasma structures to remain coherent and stable for far, far longer periods. And the suppression is vital because it means that once charge separation does occur, it can be sustained for much longer. That's foundational for building these persistent dark currents and structures we talked about.
Right, you need the separation to last.
You do. Thirdly, due to potentially higher background energies in these dark sectors, coupled with that weaker electrical charge and maybe a theorized abundance of neutral dark particles mixed in, it would be inherently easier not just to separate dark charges, but critically to keep them separated.
Unlike our universe.
Very unlike our universe, especially in the early days. Cosmological perturbations and the rapid expansion of space quickly drove our ordinary matter universe toward electrical neutrality on large scales. Sustained charge separation on cosmic scales in our visible universe is relatively rare and usually quite short-lived.
So the dark sector is fundamentally different in that respect.
Profoundly different, according to this theory. The implication is huge. In these dark plasma universes or sectors, you could have long-lived, widespread regions with mostly positively charged dark particles and distinct regions with mostly negatively charged dark particles. This persistent large-scale charge separation isn't just a minor detail. It's a fundamental characteristic that underpins much of their proposed dynamics. It's what allows them to act as the universe's architectural blueprint.
Okay, that raises a really important question then. If charge separation is so much more prevalent and persistent in the dark sector, what are the actual mechanisms?
Yeah.
How does it happen in the first place? It sounds like there must be a whole suite of fascinating forces at play, not just one single cosmic spark igniting it all.
You're absolutely right. It's almost certainly not a single mechanism, but a rich tapestry of processes all contributing. Charge separation could be initiated and sustained by several fundamental forces, things like gravitational stratification.
Like particles settling out based on density.
Sort of, yeah. Particles with different properties settling into layers due to gravity. Also mechanical forces, which, maybe surprisingly, includes friction at certain scales, and various fluid dynamical forces acting within the dark plasma itself.
Okay, so physical forces, but what about plasma-specific effects?
Right. Beyond those, specific plasma instabilities are thought to play a significant role. Let's maybe focus on two key ones, just to give a flavor of how these processes might operate. They're quite well studied in ordinary plasma, too.
Okay.
First, there's the Weibull instability. Imagine you have a plasma where the particles aren't moving uniformly in all directions. Maybe they're streaming faster in one direction than another.
Like a current or just uneven heat?
Exactly, creating an anisotropic distribution and unevenness. The Weibull instability arises specifically from these temperature differences in different directions. This anisotropy, this unevenness, spontaneously generates its own magnetic fields and, importantly, charge currents.
The plasma creates its own fields just by being uneven.
In a sense, yes. It's like the system trying to rebalance itself, smooth things out, and in doing so, it creates these electromagnetic fields and currents which can separate charge.
Okay, that's one. What's the second one?
The Biermann battery effect. This effect operates when plasmas, say, in the interstellar medium, or maybe dark plasmas in cosmic filaments collide. And crucially, their density gradients and temperature gradients become misaligned.
Misaligned gradients. How does that work?
Picture trying to stir coffee with cream, but maybe the cream is hotter on one side than the other and you're stirring it unevenly. The way the density changes isn't aligned with the way the temperature changes. This misalignment strongly drives electric currents. It literally acts like a battery, generating a voltage.
Ah, okay. So Weibull is about temperature differences in different directions, while Biermann is about misaligned gradients of density and temperature.
You've got it. Those are two big ones. But beyond these, there are other intriguing initiators proposed. Things like Langmuir turbulence, which involves plasma oscillations, can cause density fluctuations that induce localized electric fields separating charges. Or, going way back to the early universe, during or after inflation, quantum fluctuations of gauge fields could have seeded primordial magnetic fields. These tiny seed fields could then induce charge separation via the Lorentz force, especially in regions that had some initial twist or vorticity like little cosmic eddies.
Wow, from quantum fluctuations.
Potentially, yeah. Even more exotic things are suggested, like hypothetical cosmic strings or domain walls or bubble walls left over from early universe phase transitions. These could theoretically trap or repel charged particles near their boundaries, leading to spatial separation.
A lot of possibilities.
A huge number. And we can't forget the Panikkak-Rosalind effect, that's essentially gravitational stratification again, where charged particles settle differently in a gravitational field, leading to an electric field. So, as you said, there are many diverse, sometimes subtle, yet potentially powerful processes contributing to persistent charge separation in the dark cosmos. It's likely a combination of several of these.
So what does this all mean then, these sustained charge separations? They aren't just isolated theoretical phenomena sitting there, right? They must lead to something grander, something you referred to earlier as dark currents. These sound like cosmic rivers of energy silently flowing through the universe.
Precisely. You've hit on a crucial implication of that persistent charge separation. Regions where charge stays separated for long periods will naturally generate weak, yes, but incredibly long-lived dark currents.
Currents of what?
Currents composed of these self-interacting charged dark matter particles, and because you have separated regions of positive and negative charge, you'd expect oppositely charged particles to be flowing in opposite directions.
Okay, like a circuit.
In very broad sense, yes. And inherently, just like any electrical current we know, these dark currents will generate magnetic fields around them, likely helical magnetic fields wrapping around the current flow.
Right.
What's particularly stable about this configuration, according to plasma physics, is that the dark charged particles will tend to move parallel with these magnetic field lines they themselves generate. This creates what's called a force-free configuration.
Force-free, meaning stable.
Remarkably stable, yes. The magnetic forces are essentially guiding the particles along rather than pinching or disrupting the flow. And because you might have a whole series of these magnetic fields emanating from the center of these current systems, this naturally leads to a series of nested helical Birkeland currents. These would outline and form nested concentric shells of current and magnetic fields.
Nested shells, like the ones seen around some galaxies.
That's the proposed connection, yes. We'll definitely get back to that. But here's a crucial distinction, and it's key to why we don't see these directly with telescopes. The dark electromagnetic effects of these currents, they would not be felt in the ordinary matter sector.
Why not?
Because ordinary matter particles don't interact, or interact extremely weakly, with the hypothetical dark photon that would mediate dark electromagnetism. Our light, our radio waves, our everyday EM interactions simply wouldn't detect them. Only their gravitational effects would be transmitted across the sectors.
Acting as that gravitational blueprint again.
Exactly, that pervasive gravitational influence. Now, based on well-known plasma dynamics, these concentric shells that form from dark Birkeland currents, they will inherently rotate.
Why do they rotate?
It's a consequence of the forces involved, the helical magnetic fields, and the movement of charged particles within them. Think of angular momentum conservation and electromagnetic torques within the plasma system. Alfred Jay argues this could very well be the fundamental dark mechanism driving the rotation of those huge cosmic filaments we discussed.
The ones observed by Herschel.
Yes. Observations like those from ESA's Herschel Observatory seem to show large-scale filament rotation. So when these rotating dark matter structures, these shells, these currents rotate, they gravitationally tug on the ordinary matter stars and galaxies that are embedded within or adjacent to them.
The gravitational connection again.
Always the gravitational connection. We see tantalizing hints of this even in our own Milky Way. There's evidence suggesting the central bar structure is moving more slowly than expected.
Really? Why?
The thinking is it could be due to the gravitational drag or tug of a larger rotating dark matter halo surrounding it. It implies that the strength of the electric charge in these dark sectors might be exquisitely fine-tuned.
Fine-tuned how?
Tuned just right to allow for these vast, large-scale dark electrical and magnetic activities, which then influence the motions of ordinary matter primarily and consistently through these subtle but persistent gravitational interactions.
Okay, this is starting to build a really intricate picture. What's fascinating here is, how do these dark plasma dynamics actually contribute not just to the grand-scale cosmic web, but to the creation and, critically, the rotation of individual galaxies? We're talking about the very spin of a galaxy like our own. How does that intricate process, going from a cosmic filament to a spinning galaxy, actually begin according to this model?
Right, bridging the gap from the web to the galaxy. The journey, as laid out in this framework, is a really beautiful testament to these proposed dark plasma dynamics. It seems to start with those dark Brooklyn currents we just described. Remember, they're essentially the charged dark plasma component of the larger cosmic filaments.
Flowing along magnetic field lines.
Exactly, field-aligned currents. Now, imagine the current flowing within one of these dark Brooklyn channels increases, maybe due to more dark plasma flowing in or some instability.
Like a surge.
Like a surge, yeah. As that current increases, the dark azimuthal magnetic field, the field that wraps around the current channel, strengthens significantly.
Okay, stronger current, stronger magnetic field. Makes sense.
Right. This strengthening magnetic field then exerts an inward Lorentz force on the charged particles within the current. It pushes them inwards, effectively compressing the plasma. This phenomenon is famously known as the pinch effect.
The pinch effect. I've heard of that in fusion research.
Exactly the same principle, just happening with dark plasma on cosmic scales here. It's fundamental plasma physics. A current creates a magnetic field that then pinches the current channel itself.
So the filament squeezes itself.
In essence, yes. When these cosmic filaments, composed of this self-interacting dark plasma, experience this pinch effect, they don't just compress uniformly, they can generate a concentrated self-contained packet of plasma, something called a plasmoid.
A plasmoid. Like a magnetic bubble.
Sort of, yeah. A blob of plasma confined by its own magnetic field. This pinching process naturally raises local temperatures and, crucially, creates a significant overdensity of dark matter in that specific region of the filament.
A dense knot of dark matter.
A dense knot. This localized dark matter overdensity then generates a powerful gravitational well, a profound dip in spacetime right there in the filament.
And then ordinary matter.
Ordinary baryonic matter, which feels gravity, begins to fall into this well, drawn in like water down a drain from the surrounding areas. This influx of ordinary matter then leads to the formation of an embryonic galactic structure, and potentially the conditions could even trigger the formation of a central supermassive black hole. But the key is that the whole process is initiated and profoundly governed by these underlying dark plasma dynamics. The pinch creates the seed.
Wow, okay. And this is where we encounter a critical piece of the puzzle, isn't it? A concept called the Hall effect. According to Alfred Jay's research, this plays a pivotal role in actually getting these new galaxies to spin. That sounds like a key, maybe even the key mechanism for generating cosmic motion. Can you really walk us through what the Hall effect is doing here? Feels quite technical.
It is a bit technical, but it's absolutely crucial here. You could argue it's the engine of galactic spin in this model. And it provides a really elegant potential solution to the long-standing problem of where galactic angular momentum comes from. Let's try to break it down.
Please do.
Okay, first, Let's recall the conditions inside these forming plasmoids, the ones that resulted from the pinch effect. You've got a highly dynamic environment, right? Oppositely charged dark particles are flowing in opposite directions. There are strong magnetic fields generated by the currents themselves. This inherently creates magnetic shear layers sliding past each other and complex regions where magnetic field lines break and reconnect explosively.
So a very energetic, messy situation.
Exactly, a swirling, energetic cauldron of dark plasma. Now, this is precisely where the Hall effect steps in. In any system where you have charged particles flowing a current perpendicular to both an applied electric field and a magnetic field, the Hall effect introduces a fundamental asymmetry.
Asymmetry. How?
It's because positive and negative charges are deflected in opposite directions by the magnetic field. That's the Lorentz force. This separation of moving charges creates its own electric field, called the Hall electric field, which builds up perpendicular to both the original current direction and the magnetic field. It's a standard effect used in sensors, for instance.
Okay, I think I follow the basic physics. How does that make a galaxy spin?
Right, the crucial leap. Because the positive and negative dark charged particles respond differently to the combined electric and magnetic fields within this turbulent, shearing plasmoid, the Hall effect, by virtue of this fundamental asymmetry, does something remarkable. It converts what would otherwise be a chaotic interplay of forces, just random churning, into a coherent, organized rotational coherence.
It organizes the chaos into spin.
That's the idea. The distinct and opposite sideways deflections experienced by the positive and negative dark charges in these regions of magnetic shear and reconnection create a net torque. Imagine it as the collective push and pull of countless tiny charged dark particles being subtly guided, channeled by the Hall effect, into a single, powerful, and persistent rotational motion for the whole plasmoid.
So it's not just random motion anymore, it's organized swirling.
Exactly. It's like stirring a giant cosmic soup, but the stirring mechanism arises intrinsically from the plasma physics itself, from the Hall effect, causing it to swirl in a consistent direction. This conversion directly generates a strong vortical motion within the plasmoid.
Vortical motion meaning spin.
Meaning spin, yeah. A coherent rotation. As a direct result, the dark matter within that nascent galaxy, within that plasmoid, begins to rotate. And crucially, the overlying ordinary matter, which is gravitationally coupled to it, gets dragged along and also begins to rotate.
Because gravity links them.
Because gravity links them. This isn't just proposed as a minor influence. It's presented as potentially significant. This mechanism, driven by the Hall effect in dark plasma, may be an additional and fundamental cause for the rotation of galaxies. It provides a potential answer beyond current models, which sometimes struggle to fully explain the observed rotational speeds and especially the precise alignments of galaxies within the cosmic web.
So it could solve the angular momentum problem. Where does the spin come from?
It offers a concrete, physics-based mechanism for generating that initial angular momentum right at the galaxy's birth, rooted in the dark plasma itself. It fundamentally reimagines how angular momentum is generated and transferred on galactic scales. It's a really key piece of Alfred Jay's framework.
Okay, that's a powerful idea. But is it just theoretical speculation? Or does this theoretical rotation of dark plasma driven by the Hall effect actually align with things we're observing out there? Does it match up with cosmic observations or simulations?
Well, this is where it gets really exciting, because it absolutely aligns with and potentially helps explain some of the most intriguing recent findings in observational cosmology and simulation.
Like what? Give me examples.
Okay, for instance, recent observations and detailed computer simulations, too, are indeed confirming that these massive filaments of the cosmic web, they exhibit coherent rotation. They show significant vortical motion over incredibly vast scales. We're talking megaparsecs here.
So the filaments are spinning. It's not just a gas.
The evidence is mounting that they are not static structures. They are dynamic spinning entities. And these filaments, which, according to this model, are composed primarily of dark matter, mostly dark plasma, act as crucial reservoirs of angular momentum during the process of galaxy formation.
Like giant cosmic flywheels.
That's a great analogy, storing the spin that will later be imparted to the galaxies that condense within them or at their intersections.
Okay, what else?
Computer simulations have even shown a direct quantitative correlation. The more massive the dark matter halos sitting at either end of these filaments, the more rotation was detected in the filaments themselves.
A direct link between mass and spin in the filaments.
Exactly. A concrete, measurable link between the dark matter content and the rotational dynamics of the web. And then there are the fascinating observed alignments between galaxies in these filaments. This is really striking.
Alignments. How so?
Well, large galaxies often seem to have cosmic filaments piercing right through their very center. But the galaxies themselves, their disks, tend to be oriented perpendicular to the filament direction.
Perpendicular. So if the filament is a skewer, the galaxy is like a flat disk on the skewer, spinning around the skewer's axis.
That's a perfect way to visualize it. A spherical or spiral galaxy with its magnificent arms unfurling perpendicular to the invisible filament running through its core. But contrast that with small galaxies.
What about them?
They tend to lie on the filament, meaning their orientation, their longest axis, is parallel to the filament's direction.
Huh. Why the difference?
One speculation related to this model is that maybe a secondary, smaller filament branches off orthogonally at right angles from the main filament and pierces the small galaxy center, aligning it differently. But the main point is, these alignments exist and need explaining.
And the dark plasma rotation helps explain the perpendicular alignment of large galaxies.
It provides a natural reason for it, yes. If the filament is rotating, and it induces rotation in the galaxy forming around it via gravity and perhaps the Hall effect, that perpendicular alignment makes sense.
Okay. Any other observations?
Yes. We also have observations suggesting that the material in the filaments appears to be involved in accretion flows. They seem to be continuously drawing matter in from their surroundings, often through smaller, more intricate filamentary networks feeding into the main ones.
Like rivers flowing into a bigger river.
Good analogy. And crucially, simulations show this interstellar material flows along routes that are parallel to the local magnetic fields within the filaments.
Parallel to magnetic fields.
That strong parallelism is a clear, compelling hint supporting the idea of field-aligned flows of plasma, exactly what we'd expect from these proposed dark Birkeland currents.
It fits the picture.
It fits the picture nicely. And, just to reinforce the rotation aspect again, Birkeland currents, based on fundamental plasma physics, inherently possess rotational dynamics. There are instabilities and effects that make them spin, so that provides yet another inherent source of rotation for these cosmic filaments, stemming directly from the rotating concentric shells of dark Birkeland currents within the cosmic dark matter web itself.
It all seems to loop back to rotation being fundamental to these dark structures.
Rotation seems key, and it's worth circling back here to a core belief of Alfred, Jay, as outlined in his work. He argues that dark matter, unlike ordinary matter, probably didn't undergo recombination, meaning it didn't form neutral atoms in the early universe.
Why not?
He attributes this to its hypothesized weak electric charge, and perhaps a large proportion of neutral dark particles being present. Therefore, he posits, dark matter largely remained a plasma from its earliest stages.
So plasma dynamics were always important for dark matter.
Exactly. It implies that plasma dynamics would have influenced and profoundly shaped the very structure and evolution of the dark cosmic web right from its genesis, setting the stage gravitationally for the visible universe we see today.
Okay. If we connect this now to the bigger picture, this whole dark plasma concept with its inherent rotational dynamics, the Hall effect generating spin, it seems to offer plausible scenarios for some of the longest-standing galactic mysteries. I'm thinking specifically about those puzzling flat rotation curves of spiral galaxies. They've baffled astronomers for decades, right?
Absolutely. A classic problem.
And also the really strange phenomenon of counter-rotating shells of stars within a single galaxy.
Yeah.
Can you detail a plausible scenario for how the rotation of an ordinary baryonic matter disk, like the Milky Way's disk, is directly induced by this underlying dark plasma, step by step?
Yes, the theory offers a quite coherent step-by-step mechanism for exactly that. Let's walk through it. Step 1. The threading filament. We start by theorizing that a small, rotating dark filament, essentially one of those dark Birkeland currents, a segment of the larger cosmic dark matter web threads directly through a protogalactic region, a region where a galaxy is starting to form. And critically, this filament isn't static. It's already rotating due to its internal dark plasma dynamics.
Okay, a spinning dark thread goes through the galaxy nursery.
Pretty much. Step 2. Dark plasma condensation and shell formation. Now, because of the intense gravitational well generated by the dense ordinary matter, the baryonic disk, that's beginning to form the self-interacting dark matter surrounding this disk. Remember, it has a weak electric charge. It condenses. It gathers into self-interacting dark plasma around the baryonic disk.
It gets pulled in by the ordinary matter's gravity.
Yes, and then its own plasma nature takes over. It organizes itself into nested, prolate ellipsoidal shells.
Prolate ellipsoidal, like stretched out spheres. Rugby balls.
Exactly like nested rugby balls rather than perfect spheres, at potentially different temperatures or energy levels, all arranged around the baryonic disk. Now, that initial rotating filament running through the middle, it gravitationally induces a rotation in these dark shells. It makes them spin up.
Like spinning up gears.
Kind of, yeah, a gravitational lock. And critically, the rotational axes of these dark shells are aligned parallel to the dark filament itself. This sets up the alignment we discussed earlier. You can visualize the galaxy's eventual spiral arms unfurling perpendicular to this central rotating dark filament axis.
Okay, filament spins, make shells spin. Then what?
Step 3. Torque transmission and gravitational locking. The ongoing rotation of this central dark filament exerts gravitational torques, twisting forces on those surrounding dark plasma shells. These dark shells, acting as intermediaries, then in turn induce gravitational torques on the ordinary baryonic disk of the galaxy.
Making the visible disk spin up.
Exactly, causing it to begin its grand rotation. Over time, the baryonic disk and these inner dark plasma shells become gravitationally locked or tidally locked, meaning they settle into a state where they co-rotate consistently with the underlying dark filament.
And that explains the alignment.
This detailed mechanism provides a compelling and, I think, quite elegant explanation for why galactic spin axes tend to align with cosmic filaments, that observational fact from large-scale structure surveys. It all connects back to the rotating dark filament acting as the prime mover.
Okay, let's really unpack this. The famous flat rotation curves of spiral galaxies. Decades of puzzlement. Why do stars way out at the edge rotate so much faster than expected, defying simple Newtonian gravity based on the visible stuff? How does this dark plasma model, with its active dynamics, fundamentally address that stubborn anomaly?
Right. This is truly one of the most compelling problems that the dark plasma model offers a potential solution for. The problem, just to restate it clearly, is that in spiral galaxies, ordinary stars out in the fringes, far from the bright center, orbit way too fast, much faster than predicted if you only account for the gravity of the visible stars and gas.
Leading to the idea of unseen dark matter halos just adding mass.
Exactly. The standard explanation is just adding a lot more invisible mass in a large halo. Newtonian gravity predicts star speed should fall off sharply as you go further out, but observations show this nearly constant, or flat, rotation curve. It looks like there's extra mass, or maybe gravity itself is different on these scales.
So how does dark plasma solve it differently?
The dark plasma solution lies in its unique nature, its dynamics. Because the dark plasma isn't just a static halo adding weight, but is self-interacting and distributed dynamically around and perhaps even interpenetrating the baryonic disk. Its gravitational influence, combined potentially with effects from its structure, like electromagnetic tension within the dark sector. It doesn't fall off sharply with radius.
Unlike gravity from a central lump of mass.
Precisely. Instead, a rotating dark Birkeland current, with its surrounding and interpenetrating plasma shells, would maintain a distributed mass energy density, one that effectively extends far beyond the visible disk. This dynamic structure, through its internal forces, perhaps electromagnetic tension and pressure within the dark plasma itself, actively counteracts the gravitational falloff that Newtonian physics predicts for just the visible mass.
So the plasma structure itself provides support against gravity falling off.
That's the essence of it. As a direct result, coherent rotation is induced in stars across much larger radii than expected. This means the stars way out at the edges rotate at nearly the same speed as those closer to the center, producing
The flat rotation curve.
the observed flat rotation curve. The rotating axis of the filament and shells generates magnetic fields in the dark sector and gravitational torque. The dark matter halo, being this dynamic plasma, self-organizes into these rotating shells, which then gravitationally mold the baryonic matter, aligning the stellar rotation with these underlying dark plasma dynamics. The curve is flat in this view because of this coherent electromagnetic and gravitational structuring of the dark plasma.
Is there an analogy for that?
There is, actually. It's remarkably analogous to how magnetized plasma filaments behave in laboratory settings. They can maintain rotational coherence across their entire radius due to complex effects like the EXB drift, that's the motion of charged particles perpendicular to both electric and magnetic fields, and also magnetic tension, which acts like rubber bands along the field lines.
So lab plasma shows similar flat rotation.
They show coherent rotation maintained across distances, yeah. So the idea is a rotating dark Birkeland current plus its whole ensemble of dark concentric prolate ellipsoidal shells, all embedded within a galaxy's dark plasma halo. This whole dynamic system could naturally and elegantly produce a flat rotation curve for the visible disk in an ordinary matter galaxy.
Okay. And you mentioned a difference between galaxy types.
Right, a clarification. The overall dark matter halo of the galaxy would also rotate, but perhaps at a slower rate than these specific rotating flat dark shells that are closely interacting with and interpenetrating the baryonic disk. So in a spherical or spiral galaxy like our Milky Way, we might not see obvious concentric shells in the outer dark matter halo itself, but we'd have these prolate ellipsoidal shells closely wrapped around the baryonic component, driving the flat curve.
But in elliptical galaxies,
In elliptical galaxies, which are more spherical or blob-like, the self-interacting dark plasma might be distributed more spherically around the whole baryonic component, and that configuration could lead to those observable concentric shells we see around the entire galaxy, which we'll discuss more soon. The geometry matters.
got it. And what about that other really intriguing phenomenon, the observation of counter-rotating stellar populations in some galaxies? How on Earth could dark plasma dynamics explain stars or gas moving in completely opposite directions within the same galactic structure? That seems incredibly complex to reconcile with just simple gravity.
It does seem counterintuitive, doesn't it? But this is another fascinating area where dark plasma dynamics offer a compelling and actually quite natural explanation that's difficult to achieve with purely gravitational collisionless dark matter models.
How does it work?
It all goes back to fundamental plasma behavior. Think about charged particles in a magnetic field. If you have self-interacting dark plasma embedded in a magnetic field, the positive dark ions and negative dark electrons, or their equivalents, will inherently spiral in opposite directions around the field lines. That's just the basic Lorentz force acting differently on opposite charges.
Okay, they spiral opposite ways.
Right. Now imagine an electric field is also present along those magnetic field lines. For example, you could get structures called double layers forming in the plasma.
Double layers. What are they?
They're stable, localized regions with a strong electrostatic potential difference, like a tiny battery embedded in the plasma. They form quite naturally in separate regions of different plasma potential. If such a double layer exists along the magnetic field,
It would accelerate the particles.
it would accelerate the charged particles along the field lines, but crucially, it would accelerate the positive and negative charges in opposite directions because of their opposite charge.
So you get flows going both ways along the same field line.
Exactly. This process creates what we call bidirectional currents, essentially two currents flowing in opposite directions along the same magnetic channel.
And that leads to counter-rotation.
These bidirectional currents can naturally and spontaneously lead to the formation of counter-rotating plasma flows on larger scales. In a dark plasma halo surrounding a galaxy, these opposing flows could organize themselves into nested current shells, with each shell rotating differently, potentially in opposite directions to its neighbor.
So you could have an inner shell spinning one way and an outer shell spinning the other.
Precisely. The net effect would be incredibly complex rotational dynamics within the galaxy's halo. Some regions might rotate in alignment with the main underlying dark filament, while others exhibit pronounced counter-rotation. This mechanism might just explain those observed counter-rotating stellar populations.
Where stars in the disk spin one way and stars in the bulge or halos spin the opposite way.
Exactly that kind of observation. The underlying cause in this framework is these intricate dark plasma dynamics, the bidirectional currents, the nested shells. These dark structures then gravitationally sculpt the ordinary baryonic matter, the stars and gas, pulling them into these complex, observed configurations, including counter-rotating shells. It's another testament to the sheer versatility of plasma physics in potentially explaining cosmic structures.
This raises an important question then. Beyond explaining galactic rotation, both flat curves and counter-rotation, how does this dark plasma framework help us understand other mysterious structures, like those faint concentric shells we sometimes see around elliptical galaxies? You mentioned them earlier. These are vast, delicate-looking structures, and their existence has long puzzled astronomers, hasn't it?
It really has, and this is another profound area where the dark plasma theory offers a fresh and compelling lens. The observational evidence is undeniable. When astronomers map the dark matter halos around elliptical galaxies using precise gravitational lensing techniques, looking at how the galaxy's gravity bends light from background objects, they reveal the presence of these faint but definite concentric shells.
Shells in the dark matter itself, or just visible matter?
The lensing suggests underlying mass structures in these shell shapes, extending far out. These shells can reach 2 or 3 times farther out than the bulk of the galaxy's starlight. And astonishingly, in some cases, like the galaxy NGC 3923, as many as 20 distinct shells have been discovered around just one bright galaxy.
20 nested shells. Wow.
It's incredible. NGC 7600 is another famous example. In fact, about 1/10 of all elliptical galaxies show these features clearly enough to be classified as shell galaxies. It's not an extremely rare phenomenon.
So what's the standard explanation for these shells?
The currently widely accepted speculation, the leading hypothesis, is that these shell-like structures develop during or after a galactic merger. Specifically, when a large elliptical galaxy merges with a smaller satellite galaxy.
A collision.
A collision and merger, yes. The idea is that as the core of the smaller galaxy falls into the larger one, it doesn't just sink smoothly. It oscillates back and forth around the common center before settling down.
Like a pendulum damping down.
Kind of, yeah. This oscillation sends out gravitational disturbances, ripples in the gravitational potential. These ripples then propagate outwards through the stellar debris of the disrupted smaller galaxy, organizing that debris into the observed shells of stars, much like ripples spreading on a pond's surface after you drop a stone.
So the shells are made of stars from the Eaton galaxy.
That's the standard merger model, yes. The shells are seen as transient structures, remnants of a past accretion event composed of the stellar debris arranged by these gravitational ripples. It's a compelling image, but it relies on specific, often quite chaotic, merger events happening relatively recently.
But the paper by Alfred J. It presents a compelling alternative, doesn't it? One rooted directly in the fundamental dynamics of this dark plasma, rather than solely on galactic collisions. What's his argument here? How does it offer a different, maybe more intrinsic way of understanding these enigmatic structures?
Yes, Alfred, Jay's argument offers a fundamentally different perspective. It suggests the shells might be a far more intrinsic and perhaps more elegant feature, arising directly from the nature of the dark matter halo itself, moving beyond the requirement of specific chaotic merger events.
How? Does it connect back to those lab experiments?
It connects back heavily to robust laboratory analogies, yes. As we touched on, controlled plasma experiments, especially those involving dusty plasmas or rotating charged fluids, demonstrate this remarkable phenomenon. Spontaneous self-organization into concentric shells.
Driven by plasma forces.
Driven by electromagnetic forces and charge separation within the plasma. What's key is that these experimentally observed shells are often surprisingly stable, they're nested beautifully, and they exhibit striking radial symmetry, even though they emerge from inherently nonlinear, complex plasma dynamics. This strongly suggests there's an intrinsic ordering principle within plasma that favors shell formation under certain conditions.
So the hypothesis is the same thing happens with dark plasma.
Exactly. The alternative dark plasma hypothesis proposes that the dark matter halo surrounding elliptical galaxies isn't entirely collisionless and inert, as often assumed in standard cosmological models. Instead, it includes a significant self-interacting dark plasma component.
Okay.
This dynamic dark plasma then naturally forms these concentric shells of dark matter particles through a variety of inherent plasma processes, perhaps various plasma instabilities, the formation of double layers like we discussed, maybe even standing wave patterns within the plasma.
Like sound waves, but in plasma.
Sort of analogous to standing waves, yeah. Stable patterns. And importantly, the viscosity within this dark plasma, its internal friction, he argues, would even drag along any inert, neutral dark matter particles that are mixed in. It would sweep them up along with the weakly charged dark matter particles, integrating them seamlessly into these dynamic, self-organizing shell structures.
So the shells are made of dark matter, organized by plasma physics.
Primarily dark matter, yes. These dynamic, dark, concentric shells would then serve as a pervasive template, or mold, a gravitational mold.
And the visible shells.
The visible shells we see, made of ordinary stars and gas, are simply tracing this underlying dark structure. The ordinary baryonic matter settles into the gravitational potential wells created by these dark shells, mirroring the invisible, dynamically persistent dark plasma structure underneath.
So the visible shells are just revealing the shape of the dark shells.
That's the idea. And it's truly fascinating that Alfred J. had such foresight on this. He noted way back in 2005, and I think it's worth quoting him here directly, he said, "The presence of shells in dark matter around galaxies suggests its plasma state. This is strong evidence that dark plasma is involved in interactions which can be modeled by using standard plasma."
Wow, 2005. That's quite early for this kind of thinking.
It really underscores his long-standing commitment to this plasma-centric view of dark matter. He saw the potential connection very early on.
What are the advantages of this plasma explanation over the merger model for shells?
Well, this dark plasma explanation offers several distinct advantages. Firstly, and perhaps most obviously, it doesn't require a recent specific merger event to explain the shells. Since shell galaxies are relatively common, around 10% of ellipticals, relying on recent mergers for all of them might be statistically challenging. The plasma dynamics offer a potentially continuous intrinsic process for forming shells.
So shells could form even in isolated galaxies.
Potentially, yes, or persist long after any merger. Secondly, it naturally accounts for the remarkable observed symmetry and the apparent long-term persistence of these shells. Merger remnants are often expected to be more irregular and to dissipate or phase mix over time due to gravitational interactions. Maintaining such regular, coherent shells for long periods seems easier if there are dynamically stable structures within the dark plasma itself.
The ripples on the pond fade away, but these shells stick around.
Exactly. Thirdly, it elegantly explains why some shell galaxies show multiple beautifully nested layers with such high coherence and regularity. Creating 20 perfectly nested shells from the chaotic splash of a merger seems difficult. Self-organizing plasma processes might provide a more natural path to such ordered structures.
So it reframes the shells entirely.
It completely reframes them. Not as chaotic merger remnants, but as structured, almost predictable outcomes of dark plasma self-organization, inherent to the galaxy's dark matter halo itself. These dark shells act as powerful yet subtle gravitational templates. They're constantly, gently tugging on the baryonic matter, the stars and gas, causing them to respond to these invisible molds, settling into the visible concentric shells that perfectly mirror the underlying self-organized dark plasma structure. It's a beautiful, dynamic picture.
Wow. Okay, what a deep dive that was into the hidden universe. We started with Alfred, Jay's really provocative idea of a dynamic dark plasma universe, and honestly, through exploring his research, we've uncovered how it might just be the hidden architect, the silent maestro of our cosmos, orchestrating so much of what we see.
Indeed, it's quite a journey, isn't it? From the subtle dance of charge separation happening within dark matter, leading potentially to these vast, stable dark currents, to the powerful pinch effect that could initiate the very formation of galaxies.
And that crucial rotational influence of the Hall effect, the thing that actually spins them into being.
Absolutely, the Hall effect as the engine of spin. We've explored how these interconnected dark plasma dynamics could offer fresh and remarkably cohesive answers to some really long-standing questions. Things like galaxy formation, their mysterious movements, the flat curves, the counter-rotation, and even the enigmatic, delicate shells of elliptical galaxies.
Yeah.
It truly paints a picture of a far more active, energetic, and electromagnetically structured dark sector than we previously imagined, much more than just invisible ballast.
So, what does this all mean? What's the takeaway for our understanding of the universe? It really suggests a cosmos that's far more interconnected, far more dynamic, and maybe far more electromagnetically driven, at least in the dark sector, than we often imagine. It tells us that these invisible active forces could be literally shaping the visible world around us in profound ways, making the universe not just, a collection of gravitational masses passively interacting, but maybe a living, breathing entity, alive with unseen currents and self-organizing structures.
And that raises a really important question to ponder, doesn't it? If dark matter truly is an active plasma, continuously sculpting the universe in ways we are only just beginning to grasp, and if those laboratory plasma experiments can so strikingly mirror cosmic structures, what other hidden dynamics might be at play? What other cosmic phenomena, currently attributed to entirely different forces or just left as mysteries, might actually be governed by these fundamental plasma principles operating in the dark sector, just waiting for us to discover and integrate into our cosmic understanding?
Yeah, that's a huge question. And maybe consider this. If the dark universe is truly this vibrant, electrically charged realm, how much of what we perceive as empty space is actually teeming with a silent electromagnetic orchestra, playing the grand symphony of cosmic evolution, a symphony we are only now perhaps beginning to hear the faintest notes of?
What would our maps of the universe look like if we could truly see those dark currents flowing? That's a mind-bending thought.
It really is. Well, thank you for joining us on this deep dive into the potentially revolutionary world of the dark plasma universe.